And after 4 seconds, and I'll explain why it's not 4 here in a minute. But before that, let's double check. You only had the vertex now. Number 50 was actually the one we did in class. We didn't notice.
Yeah. I know.
And he still missed it. So just double check here. 87, let me talk about that. Although most of you were okay on it, just a couple areas there. That's what the apple trees, 26 trees per acre, right? And then if you have 26 trees per acre, we get how many apples? 500. And then if you start adding trees, it's going to obviously take away from the production. So it goes down by 10. So the equation for 87 is A of X for apples, we call it. 26 plus X. I saw a couple minuses or whatever. So you're adding trees to it. And then when we add trees to it, what do we decrease from the amount of apples? So it's minus 10. So it actually be the number of trees added. Now the answer is 38, but when you solve this, you actually get what? You actually get the number 12. And they say how many trees would maximize that? Well, you have to add 12 to 26 to get 38. So you didn't get it wrong if you got 12. You just had to go back and plug that in for the total number of trees, right?
Can you go through how you solved it?
From here?
Yeah, because
Okay.
I had the right equation, but I still got a really wrong answer.
13,000, you FOIL it, go ahead and FOIL it. Minus 260x plus 500x minus 10x squared. And now just reorganize, put it standard form, minus 10x squared plus 240x plus 13,000. You can graph that. All right, as part of that, so you kind of understand so looking at the graph, but we want to maximize, since it's a function that opens down, that's going to be at the vertex. So we need to find the vertex. So we use that h equals negative b over 2a. And that's going to be negative 240 over 2 times negative 10, which is negative 20. And then that's where we get the 12. Now, I don't know what you get when you plug in 12. I forget. But it's not part of the answer, I don't think. They just said what's going to maximize. Or you can keep adding by 1 and multiplying each time until you figure out it's 14,440.
Yes, that is a possibility.
That is a possibility. Brute force sometimes works. That's okay. And that's okay. So in that case here, you get 12 for that answer. Does that answer your question?
Yeah.
Okay. Kenzie, make sense? Okay. All right. So that was 87. All right, 94. What's that equation for 94? Meg, you got it in front of you or not?
H of t equals negative 16 squared, or t squared, plus 64t plus 336.
Okay, so find how high it goes. So how high it goes would be the vertex. So when you do h equals negative b over 2a, I think we get 2, right? Negative b over 2a equals 2. And when you plug 2 in, h of 2 equals 400. So it goes to a height of 400 feet. Now, in some cases, what'd you put for part B? Do you have an answer for part B when it hits the ground? Okay, Nathan, you got an answer?
Yeah, I had 4 seconds.
All right, you got 4. All right, the actual answer we said was 7. And that's who had 6.25? Okay, do you remember how you got that?
Yeah. I think I divided 400 by 64.
What made you do that?
I did
I'm just trying to think of the rationale behind it.
64 equals 400 over time, and then I just cross multiplied it and
Okay. I was just curious where that came from, because I know there were several people that had it, and maybe in other classes as well. All right, when it hit the ground means the height's what? height is 0. And sometimes you can just double the time. Not in this case, so I gotta explain why though. So as you got 0 equals negative 16t squared plus 64t plus 336. So really you could solve this using a quadratic formula, or this one would actually factor. Let me graph this real quick. I can do it here. Let's see. Y equals, and what do I got? Negative 16 t squared plus 64 plus 330. Oh, what did I miss? Is this gonna work? Darn it. I just do the same thing. There we go. All right. So, all right, there's your graph. We're not gonna do zoom fit. We don't need that. If we take a look at the table, all right, we know it goes up to a height of what we already said, 400. So I need to be somewhere above 400. Usually you don't need to mess with the X. Usually. Not always. All right. It will, like it takes if it takes 2 seconds to get to the height, it'll take another 2 seconds to get down, only if it starts down at 0. Okay. This one actually starts up here. It starts at 336. It's hard to interpret that from the problems. If you look at the graph, hopefully it at least looks like that. Okay, you understand it starts, so I don't know if he's at the top of a building or whatever when they do this, but it goes up and then it comes down. So right there, that is the spot we want. If you can look at your table, if it hits at a nice spot, okay, it does hit 0 at 7, or we can do second, calculate 0 and hit left bound, right bound, and 7, 0. So the answer for this one would be 7. And I can see why you got 4. You just got to be careful on that. Okay. All right. Anything else on that homework?
Can you go through 83?
83. All right. Which one is that? Give me a little clue there.
It was like find the max area for perimeter is 80.
Perimeter is 80 of just any rectangle?
Yeah.
All right. Any rectangle. Doesn't the answer come back to be 20 by 20? Is that right? All right. So the perimeter is area. So the perimeter is 2L plus 2W because we're just dealing with any rectangle, correct? And so we got, let me call that the length, the width, and then 80 equals 2L plus 2W in that case. All right, in this case, it doesn't matter which one you solve for. You want to solve for the L, you want to solve for the W. Okay, you need to isolate one of them. Let's just isolate, I'm going to isolate the L. 80 minus 2W equals 2 times the length divided by 2, and I get 40 minus W equals L. Where do I go from here? What am I trying to maximize? Area, right? Area is what? Length times width. So area is length times width. And we don't know what either of them are. I just know the perimeter, but I know that the length has to be 40 minus W. So I plug in 40 minus W for the length times W, and that gives me 40W minus W squared, which is negative W squared plus 40W. Now I just use your H equals negative B over 2A, which that's going to be negative 40 over negative 2. That's where you get the 20. And you plug it in, you're going to get 20 times 20, which is 400. I can't remember if it wanted the area or not, or just the dimensions. So negative 40, 2 times negative 1, 20. Okay, we good there? All right. Let me come by and collect those tests on your guided notes. Let's go ahead and get started on section 3.2. Some properties of the graphs. End behavior and zeros are the main thing. End behavior and zeros. All right, take a look. It says at the very top, calculate for me f of -2 and f of 2. Yes, have your calculators out. We will do some graphing, all kind of good stuff today. All right, f of -2. Maggie Purdy, what'd you get?
So
12. So f of -2 equals 12. F of 2, Tony, what'd you get for that one? -4. All right, now there's nothing special about those values until you kind of look at them together. So f of -2 is 12. You don't need to copy down the graph, but here's what I'm just going to draw out. So that's somewhere near here. And f of 2 is -4, somewhere down here. Well, this kind of leads us to what says the intermediate value theorem. If f of a and f of b have opposite signs, one's positive, one's negative, right? Then there exists a point C between a and b such that f of c equals 0. Well, this should be kind of common sense once you look at this, because these have to be connected, right? And the only way I can connect them is if I cross the x-axis and create a 0. So if you come up with two values, and now when dealing with what we're graphing, zeros are very important. We want to find them. So sometimes this doesn't give me a 0, but it says, all right, I know this is 12. I know this is -4. There's got to be something in between 2 and -2 where it hits 0. Okay, so hopefully that makes sense, just kind of graphically. We call this the intermediate value theorem. Now, f of a and f of b, those are just your y values. Now, you have that, I think you have this picture, right? So it just kind of demonstrates what's going on. It could be the opposite right here, but here's one thing you're not guaranteed. It has to hit once, but theoretically it could hit more than once. Okay, so if I know that at this point right here, that's positive, and I know this point is negative, it could hit more than one time. Okay, but it has to hit at least once. So that's one of the things we're going to talk about today is where it hits the x-axis. The other thing is called end behavior. Okay, we'll hit that here in a second. All right, just general terminology here. Polynomials. A polynomial of degree n is a function of the form. Okay, there's really no other way to write it. As you start moving up in the math classes, you get more variables and more letters. A sub n, x sub n, that's your leading term. A sub n minus 1, x sub n minus 1. So basically, if this is a 6, that's a 5. Okay, if it's an 8, that's a 7. All the way down to a sub 0, which is just a constant. Okay, all this is would be something like this. F of x equals 6x to the 5th minus 2x to the 4th plus 3x cubed minus 8x plus 7. Now, you don't have to hit every degree. So it could be g of x equals 2x to the 4th minus 7x plus 1. You might not have an x cubed and an x squared. These are polynomial functions. N is a non-negative integer. That can't be a negative number, can't be a decimal fraction. 5, 4, 3, 2, 1. All positive whole numbers, okay, for polynomials. Couple properties. Domain is a set of real numbers. You never can have an x in the denominator, okay, because we have positive whole numbers. The graph is continuous. Okay, the graph is continuous. There are no holes, there are no gaps, okay, from left to right. Okay, it can't be one of those piecewise functions where it jumps. No, continuous. And it's a smooth curve. Okay, no corners, nothing goofy. Okay, everything's a smooth curve. These are the properties of polynomials in their graphs. All right, end behavior. So as you plug in big numbers, what's going to happen to your answers? As you plug in small numbers, what's going to happen to your answers? All right, we're going to look at what's called power functions first. Power function is just a constant x to a power. If n is even and a is greater than 0, so that would be like f of x equals 2x squared. G of x equals 3x to the 4th. H of x equals 0.1 x to the 6th. Just graph one of them. Just graph one of them on your graph, on your calculator. On your calculator. I'm going to put 0.2 x to the 4th power. Okay, making up another one. But they all look like what? They all look like a parabola, right? They just open up. Okay, they hit 0, 0. But they're going to look like that. That's going to be the general form. All right, how do we describe that in terms of end behavior? As x goes to infinity, where does f of x approach? So as you plug in numbers to the right, what's happening to the answers? They're going where? Are they getting bigger or smaller? They're getting bigger. So as x goes to infinity, f of x is going to infinity. So as I plug in numbers, as I keep moving to the right, the answers keep getting bigger and bigger and bigger. What happens as I keep moving to the left? The answers are also going to where? Positive infinity. Okay? All right, so that's end behavior. As x goes to infinity, f of x is going to infinity and negative infinity. All right, what about that next one right next to it? It says n is still even, but a is what? A is less than 0. And so that just means f of x is negative 1x squared. G of x is negative 3x to the 4th. H of x is negative 0.1x to the 6th. Whatever. Even function, negative number, really, what's the only thing that it does? Flips it over the x-axis. It's going to flip it over the x-axis, and it's going to open down. As x goes to infinity, f of x goes to where? Negative infinity, gets smaller. As x gets smaller, x goes to negative infinity. Where does f of x go? It also goes to negative infinity. For if it has an even degree, it's either going to both go to infinity or both go to negative infinity. All right, what's that one next to it? It says n is odd, a is greater than 0. All right, so n is odd, a is greater than 0. So that would just be f of x. A real simple one is x cubed. 1x cubed. All right, graph that if you don't remember what it looks like. All right, now what happens? Let me do this real quick. Okay, and I'm just going to use x to the 3rd. Okay, it comes up and goes through the origin. What happens as the degree goes up? So instead of the 3rd, it goes to the 5th. Okay, and let's take a look at the 7. Okay, it kind of flattens out and it gets, it gets closer to the x-axis in terms of that. Let me throw insert 0.01. See what that looks like. Okay, so see it kind of, and now it really only hits it at one point. It only hits it at 0, 0. But it kind of gives that impression it's traveling along. There's absolutely no way it can. It's just very, very small numbers. Okay, for that. So if really for anything odd, it's going to look like this. It's going to start, it's going to go from low to high. It's going to go from low to high. As x goes to infinity, f of x goes to where? Infinity. As x gets smaller, what's happening at f of x? Negative infinity. All right, what happens if we make this negative though? F of x equals negative x cubed. What happens to the graph? Okay, so actually it's going to start up. Okay, it's going to start high and go low and go through 0, 0. So as x goes to infinity, where's f of x going? Negative infinity, and as x goes to negative infinity, f of x goes to positive infinity. All right, that's for power functions. There's just one term. But what about like f of x equals, 7x to the fourth minus 2x squared plus 3x minus 2. Just looking at that, where's its end behavior going to be? Okay, are they going to open up, open down? What's it going to look like? Okay, and it's really pretty straightforward. The end behavior of any polynomial. Yep, I think we're on the next page. Okay, the end behavior of any polynomial is determined by its leading term. That's all you got to look at. And the only thing you got to make sure is that if it's out of order, you got to rearrange it. The leading term is the highest degree. So if this is, written as 4x minus 7x cubed plus 3 minus 8x to the fifth, what's the leading term of that one? It would be negative 8x to the fifth. So understand you got to rewrite it. Don't just say, oh, that first term is 4x. No. Well, this leading term here is just 3x cubed. Well, what's the end behavior of 3x cubed? It's a positive 3. It's an odd function. So it goes from low to high. Now, when you write this end behavior, when it says describe the end behavior, this is what you do mathematically. As x goes to infinity, where's f of x going? Okay, you got to do that piece. So that means it's going to positive infinity, right? And as x goes to negative infinity, where's f of x going? It is going to negative infinity. Now, I don't know. There's a lot of stuff that could be going on. We know the power function looks like this. This is just describing the end behavior, which means there could be all kind of stuff going on in between there. Okay, I just know here it's going down and here it's going up. Other stuff could be going on. This is just describing the end behavior. All right, describe the end behavior of that one. Okay, negative g of x equals negative 3x to the 6th plus 4x cubed minus 13x plus 1. Peyton Rader, where's the end behavior? What's it going?
As x goes to infinity, f of x goes to negative infinity.
Okay.
And as x goes to negative infinity, f of x goes to negative infinity again.
Good. They're both going to negative infinity. You're only looking at negative 3x to the 6th. If you need to look at the other side, that's fine. They're both, but it opens down like this, just a parabola open and down. But, there's going to be more stuff in there going on between there, okay? So just end behavior. End behavior, that's all we look at, x to the 6th, and then the constant in front of it. All right, degree has a huge impact on what's going on, okay? If f of x is a polynomial of degree n, okay, then f of x has at most n real zeros. The graph of f has at most n minus 1 turning points. Okay. Now, I'm just making this up. So if f of x equals 2x to the 4th minus 3x cubed plus 7x squared minus 8x plus 1, it is the highest degree would be n. So it's 4th degree. So at most, how many times can it hit the x-axis? At most, it can hit it 1, 2, 3, 4. This end behavior, it's a positive 2, right? So they both go up. So I don't know all the details, but it's got to hit those 4 points and it has to go up. How many turning points does that give us? 1, 2, 3. So you can only have 3 turning points. If you got another turning point, they would have to hit the axis again, and they can't hit it 5 times. You can only hit it 4. Okay. All right, now this next part isn't on your guided notes. Okay, use your calculator, graph that, and find the zeros. Okay, find where it hits the x-axis. So graph x cubed plus 5x squared plus 2x minus 8. All right, so let's see here. We got clear that. So I got x to the 3rd plus 5x squared plus 2x minus 8. And we hit graph. Okay, where's it hit at? It's at -4, -2, and 1. All right, so this is -4, -2, 1. All right, good. Now, go to y2. Go to y2 and graph this one. Okay, what's the difference? Ryan? No, they're exactly the same, right? So you got x plus 4. How can that happen? That's crazy. X plus 4 times x minus 1 times x plus 2. So you look like, hey, there's nothing new. If you want to know if they're really the same, go to your table. Y value's got to be the same. Now, we said, where are the zeros at? We said they're at -4, 1, and -2, right? Which form is it easier to tell where the zeros are? Second one, right? So if it's written like this, yeah, you just say, well, solve that. X equals -4, x equals 1, and x equals -2. We got that. Here, so our job eventually is going to be take this to convert it to that. All right, because if we have it in this form, hey, I know it hits at -4, I know it hits at 1, I know it hits at -2. All right, we want to take a look at the zeros and what happens at the zeros. So a lot of times it's going to be easier to write it like this. So in this next case here, I'm going to put it in this form, but some of them are going to have squares. Let's see what you got. Yeah, that would be the first one there. Let's kind of do these together. x plus 3 squared times x minus 2. Graph that. Graph that on your calculator. And don't draw it on your, don't draw it yet, just graph it for a second. We want to see what happens at the zeros, okay? Now I know for this first one, I know it hits at -3. I know it hits at +2 because those are the zeros, right? Now I'm not really concerned with the details. I'm more concerned just with the shape and what happens at the zero. Well, right here, it starts low, comes up, it hits it at -3, and then it comes back down, and then it goes through 2. Correct? Yours looks similar to that. All right, draw that. I'm not looking for the exact y values. I just want the general shape. So even though it goes off your screen, just give me the shape. So we want to look what happens as we change the exponents. What happens to the graph? So these are all have x plus 3 and x minus 2, but they're all going to be somewhat different. All right, graph the second one. Graph the second one. Okay, it hits at -3, right? It hits at 2. Now, what happens at -3, though? Okay, so you look at it. Does it go straight through? No, there's a little bit of a change of direction there. We call that a bend or a squiggle, depending on how you want to refer to it. But you need to learn how to draw it, because it doesn't go straight through. Does it go straight through the other one? Yeah. And this one actually starts up, and it comes down, and it goes through that point, and it goes up through. Okay. Why does this one start up? This one ends at both going the same direction, right? Where the other ones, the one started low, went high. What causes that? Okay, Jacob.
The first set is cubed, and then the second set has an exponent of 1. So if you add them, you get an even number.
Okay, right. Yeah. What is the final degree of this one? The final degree of this one would be what?
3.
Not number 2.
Oh.
The final degree would be, like, if you multiplied everything out together, this would be x to the 4th power. Yeah. Yep, and this would actually be x to the 3rd power. So this is really a 3rd degree function. This is the 4th degree because I got x cubed and another x. What degree will this bottom one be? This will also be 4th degree. All right, graph this one. You don't need to, you can erase the others as well. You don't need to all graph them on the same. Okay, you can erase the others. I know it's going to hit at -3. I know it's going to hit at 2. What's going to happen there? At -3 and 2, they're both squared there. They're both squared. All right, now it goes off the page a little bit, but you kind of have to have the general idea what's going on. So it hits at -3, it comes down, it hits at -3, and then it turns, and then it comes back, it hits at 2, but it doesn't go through. It doesn't go through. All right, we call that a bounce. Okay, it bounces off of that point. Doesn't go through it, it hits it and comes up. What causes it to bounce? What part of the equation causes it to bounce? Okay, we figured that out yet.
The square?
The squared. If you have a squared, because like right here, we had x plus 3 squared, it bounces. If it is 1st degree, it goes straight through. And what is a 3rd degree Power do? Makes a squiggle. Okay, gives it a bend or gives it a squiggle. Second degree makes it do what? Bounce. Okay, and actually any even degree makes it bounce, as you see that. Hold on here. What do you got below there? Don't you have something? Talks about multiplicity of the zero. All right, where is that at? Let me see something. Do I have it? All right, we'll go there. So multiplicity of 1. The graph goes through the point, continues on its path. Okay, goes through the point, continues on its path. There's no change in its direction. Okay, and you saw that in several of those cases. All right, if it's an even multiplicity, 2, 4, 6, 8, what happens? Bounces. Okay, that's where it bounces. Graph, and then, technically the graph touches but does not cross the x-axis. Doesn't touch it, it hits it. Boom. Hits it and bounce. With bounce or however you want to refer to it, that's fine. And what happens with an even or an odd multiplicity bigger than 1? You get that squiggle. Graph crosses the x-axis, but we call it a squiggle or bend for that one. And then this is just an FYI, that bottom one, the higher the multiplicity, the flatter the graph is at that 0. That's kind of what we were trying to show earlier. Like you got x to the 7th, it kind of gets really flat around the 0. Or if you got x to the 6th, it's going to be a little bit flatter as it approaches that point. Okay. All right. Once you get that done, we're done for the day. No homework over the weekend. Thank you.